In this lesson, we are going to keep going with chapter 1, and we're going to look at 1.4, which studies potential energy diagrams. This kind of follows up from our conversation about activation energy. So we're going to be looking at the activation energy, we're going to be looking at energy profiles for a reaction, and talking about enthalpy and bond energy and things like that. So we're going to look at potential energy diagrams. Some of the goals for this lesson is to define the following words: enthalpy, bond energy, endothermic and exothermic reactions, and activated complex. We're going to differentiate between thermochemical equations and delta H notation. Again, this is a little bit of a review from last week. We started looking at it then. We're going to draw potential energy diagrams for both endo and exothermic reactions, identify the activation energy and change in enthalpy from potential energy diagrams, and then finally we're going to look at how a catalyst will affect the potential energy diagrams. And I might add that fourth point there, we're also going to be looking at forward and reverse reactions. So a lot what we do in Chemistry 12 is going to be looking at reactions that are reversible, where they can go one way, but then we can also reverse them and go back the opposite way. So I've just put kind of some pictures here to show you some sources of energy. On the top left, you can see a furnace where we're burning fuel to make heat. The second one there is we've got a battery where we are taking chemical energy again, and we're going to convert it to heat, running a current. And then we've got a 4-stroke engine there as well. So these are some of our sources of energy, and I've put those on the page just to show you that we can take our chemical energy and we can actually convert it to heat. So that's most commonly converted to heat. We use delta H to symbolize a change in energy available as heat. So I'm just going to put a couple of notes on the board about that. So if you're wondering where the delta H comes from when we're talking about enthalpy, and this is the delta sign, so change in. So we're commonly converting that chemical energy to heat. We're going to be talking about converting chemical energy to electrical energy, chemical energy to heat. We'll look at converting electrical energy to chemical energy later on as well, but we're looking at that changing energy and how we move it around. So we're going to define on this slide what enthalpy is, and I alluded to it in the last thing. This is potential energy that may be given off or absorbed as heat. Related to that H. And we know that that delta H is equal to change in enthalpy. So we're going to be using enthalpy. We're going to be plotting enthalpy on a diagram. We'll look at some of the potential energy and looking at how that heat is absorbed or released in a reaction. So on this page, we're going to be kind of looking at two different types of reactions. We're going to be looking at exothermic reactions and endothermic reactions. So those are the two that we're going to be looking at. Electrons all have potential energy. And anytime we are breaking a bond, like you can see down here at the bottom, breaking a bond requires energy. The reason breaking bonds requires energy is we have to move the electrons farther from the nucleus. So the nucleus is positively charged. The electrons are negatively charged, so they're attracting one another. So if we want to move it farther away, it's going to take energy. When we're forming a bond, that will release energy. So we have energy exiting from that system when we're releasing, when we're forming that bond, releasing that energy. So that brings us to the definitions of exothermic and endothermic. When we have exothermic reactions, this is where the energy released is greater than the energy absorbed. So energy is exiting, and I use EX, exiting. So energy is released from the system. That means that our delta H will be negative. In an endothermic reaction, our energy absorbed is greater than the energy released. So energy overall is absorbed, or enters, EN, endo, enters. So I'm going to put entering, just as my mnemonic to remember that. And the delta H is going to be positive. So we can see the two examples of potential energy diagrams right at the bottom here. On the left-hand side, we have an exothermic reaction. So here's the potential energy. This represents the energy that's held in the chemical bonds. When we have a reaction taking place, we have to overcome this little hump here. And then once the reaction is over, we move to this new level. And you can see that energy was released from the reactants to the products. That delta H is negative. With an endothermic reaction, my reactants have kind of low potential energy. Here's where my reaction is taking place. We get this big kind of conglomerate taking place, big mashed together molecule, and then the products have higher energy than the reactants. That delta H is positive. So there's my endothermic reaction. We can represent this in a couple of different ways. So if we have an exothermic reaction, we can represent this with a thermochemical equation. So I'm going to show you a thermochemical equation. So my thermochemical equation, we write the energy term right within the chemical reaction. So if I had something like nitrogen gas and hydrogen gas, and they're reacting to form two molecules of ammonia, I'm going to write that we've got energy exiting that system by putting it on the product side. The other way I can write this is in delta H notation. With delta H notation, we write our chemical reaction just like normal, and we put the energy term outside of the reaction. So there's my ammonia. And right outside the reaction, I'm going to put delta H is equal to, delta H is negative, so I'm going to put negative 92 kilojoules per mole. Now you'll notice that we've got two different signs here. I've got a positive when it's in the reaction, and the positive is because it's on the right-hand side. I'm showing that it's a product. I've got this negative here to show that that energy is exiting the system. It's kind of like when we were expressing reaction rates, and we expressed our reaction rates always as a positive, but we might show one of the products being formed. So that's kind of why we do that. With the endothermic reaction, you'll see how it kind of differs. With our thermochemical reaction, I've got two molecules of hydrobromic acid, and I've got this time my energy going into that system. So you'll notice that it's positive still, but it's on the left-hand side. And I can write that in delta H notation as well. I'm going to put the delta H outside, and this time I'm going to write that it's positive 72.2 kilojoules per mole. So the only thing we have to kind of look at is with that delta H being negative, that means that energy is exiting the system. The kilojoules per mole, that energy term, is going to be on the right-hand side, on the product side. On the endothermic reaction, that energy is entering the system, so it's going to be on the reactant side, or my delta H is going to be positive. Okay, the last thing that you will have noticed probably on the potential energy diagram is that middle bit where it went up. So when we were graphing this, we kind of had this term that kind of went up and then leveled off again. This middle bit here is called the activated complex. And what the activated complex is it's an unstable configuration of electrons. So those electrons are getting pushed too close to the molecules. That leads to really, really high potential energy. My kinetic energy is actually slowed down because everything is smushed together. And it's very, very unstable. Everything is in transition. So this has very high potential energy. Okay, just using PE to represent potential energy. So here on the left-hand side in this picture, this is my reactants. Those reactants, when they all come together to react, you can see they all get smushed together. I have very, very little space between the hydrogens and the oxygens. All of those electrons are very, very close to the center. Leads to very, very high potential energy. Everything slows down as those electron fields are overlapping. So they slow down as they're approaching each other. That's where the activated complex is. And then everything splits away and your product particles will kind of fly away everywhere. And so there's the end reaction. So here's some of the information that we can gain from a potential energy diagram. First thing that we can look at with a potential energy diagram is this side on the left-hand side here is representing my reactants. So I've got A plus B. Those are my reactants. And this energy right here from 0 to 40, this represents the potential energy of those reactants. So the potential energy of the reactants is equal to 40 kilojoules in this particular graph. Potential energy of the products goes from this end line here. So here's my products potential energy, and this is a little bit lower, so I have 20 kilojoules. Third thing that we can do is look at this graph, and here, right up at the top, this is my activated complex. So with the activated complex, you can see that the potential energy is equal to 100 kilojoules. Now these numbers are going to become important when we're looking at the activation energy and how much energy change we have, or change in enthalpy. So my activation energy is going to equal the potential energy of the activated complex minus the potential energy of the reactants. So EA represents activation energy. Activation energy is equal to the potential energy of the activated complex minus the potential energy of the reactants. So for this particular potential energy diagram, we can just go ahead and calculate that. Potential energy of the activated complex is 100 minus the potential energy of the reactants, which is 40. That gives me 60 kilojoules. Now my energy change, what I'm looking for with an energy change is my change in enthalpy, delta H. And my change in enthalpy is equal to the potential energy of the products minus the potential energy of the reactants. So the potential energy of the products is 20 kilojoules. Potential energy of the reactants is 40 kilojoules. So you're going to see here that I end up with negative 20 kilojoules, and that makes sense because this is an exothermic reaction. So the last thing is I can predict whether this is a endo or exothermic reaction based on this potential energy diagram. I'm going to suggest that you pause right now, do some of the practice problems on page 41 of your books, come back, have a chance to discuss them, and then we're going to cover catalysts. Okay, lastly here are the catalysts. So catalysts provide an alternate mechanism and they have lower activation energy. So that's what a catalyst is. You may have heard that they speed up a reaction, and that's true, but we got to look at beyond just speeding up. Why do they speed up the reaction? So they provide an alternate mechanism with lower activation energy. So when we are trying to figure out what the activation energy of the catalyst is, we always measure from the highest peak. So you can see that we've got this kind of bumpy series of steps here with my catalyst. And catalysts often work with a series of steps, and each step will have a little bump. We are always going to measure from the highest peak. So in this particular one, I would take my activation energy from where I have XY all the way up to the top. So I'm going to take from the highest peak down to XY, and that's going to be my activation energy. One other thing about catalysts is catalysts are unchanged after the reaction. So it's a little bit different than the definition that we gave you in grade 11, where we said that catalysts don't change during the reaction. Catalysts may change throughout the reaction, but by the end of the reaction, they are regenerated and are unchanged. And they can go on and catalyze several different reactions. And you can try the quick check, so work with a partner or work in groups on page 43 of your workbook. Try and do some of these quick check problems, see if you can identify all of these different things. For this quick check, just be careful because some of them are asking for a reverse reaction. Okay, so watch out for that reverse. If we're looking at a reverse reaction, you can pretend that this is the reactants and these are the products. So the reactants on the right and products on the left. That can be a little bit tricky, but if you know that, then you can probably do these quick check problems very quickly. Okay, and that is it for this lesson. So homework assignment for this is to try the in-class activity on page 31 to 32. Read pages 24 to 29 in your workbook. So if your workbook has different pages than mine, we're just looking at reading section 1.4. And then right at the end of section 1.4, complete questions number 1 to 4 and 6 to 8 on the pages right at the end of the chapter. Thanks, guys.